waiting to talk with you today, and I will present to you now. So, Professor Retallack is his research group is dedicated to the proposition that soils have a fossil record like other living things. Past studies have considered that the
Oh, you've cut out on me, Marianne.
Now we are back. Okay.
You cut out on
And
me.
Professor Retallack has a lot of papers about Precambrian and Cambrian explosion on land. Gente, Precambrian life on land and Martian paleo with field work in Newfoundland and Australia. Is it right?
I'm good. Yes. Did you want me to start the talk?
Yes.
What do I do? How do I get the slides? Do I just press this? Press this? I uploaded slides. How do I get into them? Oh, share screen. There we go. The browser has blocked my screen. Let's try this. No, that's not it. Present. Slides. Snowball onset. No. So I need to share screen, right? Share screen. Can you see that, Marianne? Marianne, are you there? Hello, Miriam, can you hear me? Do I need a login code or? Ah, dear. Not syncing.
Professor, are you hearing me well?
Yeah, I'm here. I'm trying to sort of sync, and I'm not logged in either. I'm not familiar with this platform.
No, we have some problems here with our internet. So sorry for that. But
I
now we are back. I perform a brief presentation of your work here in Brazil, and it will be very interesting because we have a lot of students in paleontology in
Right.
various degrees. So thank you again, Professor, and sorry for these issues that we have in the
Oh,
morning.
you don't think it's going to work, huh?
No, but I think now it will work. Are you able to, you want to share your presentation?
Yes, I'm ready, and I'm trying to bring it up.
Okay, okay, I will try here to help you.
I uploaded. Ah, you did it. Well done. Thank you.
Okay.
I think we're good. Well done. There's a needed
Okay,
some
but,
direction
but
for you.
you are able to change the slides if you want.
Let's see. Can I change the slides? Let's see.
It's working.
Let's try. No, I can't change the slide. So I'll just.
Okay.
Oh, yes, I can. There it
Yes,
is.
you can. Okay.
A little button comes up here. This technology is lovely. It's a
Yeah.
different platform that I'm used to, but thank you so much. So I'll just launch in, right?
Yes.
Snowball Earth, of course, is a rather remarkable period of Earth history where many people think that the whole world was frozen over. And the evidence for that is pretty compelling and in many places. And it's of great interest to us if we're interested in the habitability of our planet, because if the world really did froze over to this extent, even to this extent shown here, it'd be very hard for life to survive. Whoops, here we go. Now, in the long term, it's not too surprising. I've lost the slides now. It's not too surprising that the Earth was cold. And that's because if you look at this graph here, which goes back 4 billion years, the sun really only turned on at around about 4 billion years ago. And when it first turned on, it was a pretty dim bulb. Stellar luminosity, we know from the study of stars in the whole solar system and the universe, increases through time from a very dim bulb where the Earth's temperature should be about minus 40 degrees centigrade through to the current temperature over 4 billion years. We know that can't be the case for our Earth because we have evidence from paleosols. And that wiggly line is what we estimate was the Paleosol temperature back through to about 3.6 billion years, where we have a record of Paleosols. And furthermore, that time is interrupted by ice ages, which are the blue bars. We also know, since we have minerals such as gypsum and we have fossils, that there's an upper limit for life on Earth, about 60 degrees centigrade. And because it froze over completely, we can't go too much below zero. It would actually freeze over completely. And what I want to talk about today is the evidence that we have from paleosols that there has been quite a good control of control of our, dear me, I've got a, yeah, there we go. There's been quite a strong control of temperature. Oops, cancel. Through time. Are you adjusting it? You're good. Now, this whole snowball idea was actually invented by a great hero of mine by the name of Sir Douglas Mawson. He was a professor of the University of Adelaide for many years, and also the participant in the Australian Antarctic expedition of 1909, when the Australians, including his professor, Tanit Edgeworth David, another geological hero of mine, made it to the magnetic South Pole, which is not quite so dramatic as the geographic South Pole, the one where Robert Falconer Scott perished in 1913. But Sir Douglas Mawson discovered this snowball idea in the Flinders Ranges of South Australia, which is a place where I have spent many, many productive years researching Ediacaran environments. Now, Paul Hoffman, formerly from Harvard and now at the University of British Columbia, has been documenting this snowball Earth idea in many places all around the world, starting from the South Australian occurrences, but particularly in Namibia. Here are some slides from him of dropped pebbles, pebbles that presumably dropped out of the ice that was on the surface of the ocean. And he envisaged the whole ocean was covered with ice, which is a bit of a problem. Now, I don't think the whole Earth was covered in ice, because we can see both here at a place called Hallett Cove near Adelaide, South Australia, that there were ice wedge, sand wedge paleosols, the kinds of soils that we now get in the dry valleys of Antarctica. There's a picture above, and then my geological sketch of it, and then a reconstruction. There was bare earth exposed, particularly in tropical regions, even during the peak of this snowball Earth event. That's not to diminish the idea that the snowball event was pretty significant. To get a climate like the dry valleys of Antarctica at the tropics is still a pretty big climate change. And the question is, why? Well, it turns out that every explanation pretty much has to do with soils and weathering. The basic idea is that if we ramp up weathering, we can consume carbon dioxide as the main weathering acid, carbonic acid. If we can increase weathering somehow, that will cool the planet. And there are several ways to do that. One way that Paul Hoffman likes in particular is that at that time, the different continents were largely in tropical regions. So if all the continents are clustered in the tropics and there's virtually no continents in high latitudes, that will increase weathering, because the tropics are, of course, a lot warmer. Well, that doesn't really work all that well, because we know at this time that even the tropics were really pretty cold. And furthermore, here is the plate tectonic reconstruction for both the Marinoan and the Sturtian, 720 and 635 million years ago, which shows that, well, there was a pretty good spread of continents. They weren't really only in the tropical regions. Other people have thought that perhaps there were huge volcanic eruptions, and that all of this fresh volcanic material enhanced silicate weathering. That doesn't work out all that well either, because there really aren't any big volcanic eruptions that we can see that correspond with this event. A third, more intriguing idea is that marine algal blooms consume carbon dioxide. That for some reason, maybe just evolution, the oceans became so much more productive. But even if they could evolve productivity by more sophisticated organisms, they still needed to feed those organisms with basic nutrients: calcium, magnesium, sodium, potassium, and particularly phosphorus, by enhancing weathering. My idea, number 4 here, which I'll try to persuade you is the correct one, is that there was an evolutionary event, all right, and it was an evolutionary event of creatures on land. That this was a time when lichens first evolved, and these lichens accelerated weathering on land. The marine algal blooms were a byproduct of that accelerated weathering. The weathering on land is what consumed CO2 and brought down the big chill. Now, I've done fieldwork on this in several places. This is some fieldwork I did in Central Australia at a really lovely place called Ellery Creek. It's actually immediately below the Arionga tillites, which in this area are the Sturtian tillites, the big glacial deposits of the first big episode of snowball Earth. What I discovered there was really pretty interesting. This is a pretty busy slide, but all of these bars here in column B are paleosols, and some of the features of the paleosols, their calcareousness, you can see in column C, and in D you can see the color, which is largely red. This is a whole sequence, several hundred paleosols. Many of them have rather light carbon isotopic composition. That's in column E, and oxygen and carbon isotopic composition in column E and F. And the organic carbon composition is also very, very light. They're quite heavily weathered, and we have ways of getting paleo productivity and CO2 from them as well, and that's in columns L and I and J. This is what a paleosol looks like. We have them in outcrop and also in core. In a core, Australia has these lovely core facilities. This one was in Alice Springs. You can see a sharp top to the paleosol, then red intensely weathered clay material, and then you go down to these rather light colored calcareous nodules. There are four kinds of paleosols, and I did a detailed chemical and mineralogical analysis of them. Two kinds are especially relevant. Some of them are just very weakly developed paleosols and not too significant. But there are some paleosols that have gypsum. Those are what we call gypsids. And some that have calcium carbonate nodules. Those are what we call calcids. I gave them Aboriginal names because I feel like this is the First Nations lands dating back to about 800 million years before present. Alkingi and Akangera from the local Pitjantjatjara Aboriginal language. Now, to summarize what we think is going on here in this whole sequence of paleosols, we can get the productivity of a soil in terms of the amount of carbon in it, and that is in this left-hand column. And we can see that there's a slow increase in soil productivity. And that was largely because we went from a regime of largely gypsids with gypsum to a regime of largely calcids. We know from studies of the modern Atacama Desert, and I'll talk about that in a little bit, this is a very big increase in soil productivity, in soil carbon dioxide, which means that these soils became suddenly a lot more deeply weathered. The idea that maybe the area in Central Australia drifted into tropical regions is not supported because we have paleopoles from different levels in this sequence in Central Australia, and nothing much was happening. Atmospheric CO2 did actually, in fact, get drawn down, but only a little bit. And volcanism is found on only a few horizons and doesn't appear to be particularly significant. What is significant, though, is that in these calcareous paleosols, we found fossils. The actual fossils are shown in the bottom here, but I've got some sketches of them in the top. Some of them appear to be algae, like number A, and perhaps B and C, but D is a very interesting looking fossil that appears to be like a lichen. It's a quilted fossil with a rather detailed fractal structure of a central stipe and then laterals. E and F are trails, which I believe are trace fossils of slime molds, these very peculiar amoebae that are aggregating and moving along as a slug. It's a very interesting kind of a creature, the slime mold, like modern Dictyostelium. What we have then in these paleosols is evidence of not just microfossils, not just single-celled creatures, but complicated organisms living on land at about the time when we see evidence of increased productivity on land. I also did the same sort of work here in the Grand Canyon on a hike in 2019, and we are looking at a level in the Grand Canyon which is hard to get to. It almost killed me, literally. That'll be a story for another day. We actually go below the classic Grand Canyon sequence, which is many people know even from textbooks in Brazil, and I remember as a boy in Australia, it goes only back to the Cambrian. If you get below that, we find below those flat-lying rocks, there's a slightly dipping sequence of the Chua group, which is about 800 million years old. And the Chua group, like the Ellery Creek sequence in Central Australia, also has paleosols, not so many. Most of the Chua group is a gray shale, and it's a shallow marine sequence. But there are many levels where there are red beds. And these red beds include paleosols, like the one I show in the top right here. Sharp top to it. Look how well that material has been bioturbated. It's been actually made more massive. It's lost its bedding compared to the sandstones that are on top of it. It's quite a well-developed paleosol, and those little spots that you can see low in the profile are calcareous nodules. So once again, we have calcids. In the different columns, we can see different chemical values of carbon isotopes, of totaline versus iron, of the kaolinite, which appears to be pedogenic, and some biomarker evidence that these were living soils that were exposed in the time before the onset of snowball earth in Arizona. We pulled apart the soils in great detail, 71 paleosols of 7 kinds, not hundreds as in Central Australia. And we found that there were, again, 2 different types. Some of them were calcids, and some of them were gypsids. Some of them had calcic horizons to them, and some of them had gypsic horizons. We know from studies of modern soils that calcic paleosols and soils are much more productive than gypsic paleosols and soils, which represent extreme deserts. Here's a summary for Arizona. Soil productivity did increase. We went to calcic horizons on several horizons. We start to get more and more eukaryotic biomarkers turning up just after the last calcic horizons. Weathering shows a steadily increasing, decreasing trend at the very top, but increases right where we get a lot of eukaryotes in the sequence. Continental drift actually did work to put the area into a lower latitude, which is quite a surprising result. So that would have worked to increase the weathering effect in these soils. Volcanism was pretty static with some sporadic tophaceous horizons. And in fact, we can date this sequence really quite nicely by using zircon dating on fresh volcanic dust. What really surprised us, though, was when we started to macerate, in other words, dissolve in acid some of these paleosols, all this wonderful stuff started tumbling out of the rock itself. There are some cyanobacterial fossils, that's A to C, but there are also stouter chords like D, and chords that seem to have intervening spores like E, and these strange vesicles like F. These are fungal. This suggests to us that there were not only prokaryotes like cyanobacteria, but also fungi in these soils. The really lovely thing that we found from G through K was that there were thecamebans. These are testate amoebae. Now, these have been known from this particular area for quite some time and thought to be marine. However, that was always a bit of a puzzle because thecamebans don't really live in the sea anymore. They live on land. And yet here we find them on land just prior to the snowball Earth. They are indications, along with everything else, that there was a big step in biological productivity of soils on land. And then finally, we only have fragments of it, but there are multicellular lichen-like fragments of these parenchyma-like cells, which are invaded by what appear to be hyphae. and that is that lower 3 panels there. We don't really know what kind of a lichen was, what kind of a fungus it was, but multicellular creatures were living on land prior to the Snowball Earth, just as in Central Australia. So here's the reconstruction for both Australia and Arizona. Australia on the left, Arizona, the 2 panels on the right. In both places, we seem to go from largely gypsic paleosols of extreme desert, similar to extreme desert soils today, to largely calcic paleosols, which are of the more moderate desert kind of soil today. Now, what we're talking about here then is not microbial mats, not stromatolites like in the left panel here. We're talking about microbial earths. We're talking about living soils. The search image, of course, for stromatolites and marine microbial scums is quite different from that of a microbial earth in which the creatures are living within the soil profile itself. They have very distinctive surface textures, but they also have a significant thickness, and the organisms living down there are respiring CO2 and increasing the biological productivity of the soil, which increases the amount of weathering and increases the amount of carbon sequestration dramatically. We know about this from the Atacama Desert of Chile, where the microbiome has been studied in detail. In the Atacama Desert, in the extreme hyperarid parts of the Atacama Desert, there are prokaryotic cyanobacteria and actinobacteria. Actinobacteria, which used to be called actinomyces and thought to be fungi, are actually prokaryotic decomposers. They have a role in ecosystems very similar to fungi. In other words, they decay things, but they are prokaryotic, simple creatures and very primitive. We have evidence that they go back about 3.5 billion years at least. But the calcic soils, on the other hand, they are the ones with eukaryotic algae, lichens, and fungi, and even a few vascular land plants in the Atacama Desert, and indicate an order of magnitude more productivity, more production of carbon dioxide, and much more weathering, deep weathering. That's what you need to really pull CO2. You can pull CO2 out of the air in 2 ways. One way is to put it into the organisms themselves. That's biosequestration. The other way is weathering. You can consume the carbon dioxide in making carbonic acid, which then is used to liberate nutrients in the soil. Oh dear, one of my panels has disappeared. That's unfortunate. But what I want to run through now quickly is that the Snowball event of the Maranoan and Sturtian about 600 to 700 million years ago was only the first in a series of ice ages on Earth. And the ice ages seem to correspond with major advances in evolution. In the Snowball case, I've made a case that it was the transition from prokaryotic gypsiferous soil communities to eukaryotic calciferous soil communities. There was another ice age, of course, in the Ordovician, and I believe that was created by the evolution of land plants, which accelerated weathering on land and also accelerated the biosequestration of carbon in their bodies. Here's a reconstruction of a community of early land plants from the early Ordovician of Tennessee, which I described a few years ago. Here is another ice age, of course, the Gondwana ice age, which you have probably heard about from the Brazilian Paraná sequence, when glaciers descended not only on Brazil, in fact, it started in Brazil, but migrated over all of the Gondwana supercontinents, ending up in my home country of Australia in the Permian. That ice age corresponds in time with the evolution of trees, starting in the Middle Devonian and then culminating in the Permian. That had an enormous effect. Not only in an increase in biomass, you can see on the top line the sizes of trees through geological time from the Cambrian through to the Carboniferous, but even more profoundly on the depth of weathering in the soil. The depth of weathering to the calcic nodules, even in calcic paleosols, the extent of hyphae reaching further and further into the soil to depths of about 2 meters or so. And then with the advent of forest, the development of these thick clay horizons of these alphasols, ultrasols, and other forest soil types for the first time in Earth history. This biological invention of forest soils and of trees had consequences as an ice age. And then finally, the ice age of the Pleistocene, what caused that? I believe that was due to the evolution of sod grasslands. Here are 4 panels here showing the early Miocene, about 19 million year old, advent of sod grasslands with their very distinctive crumb beds, very, very distinctive soil structure, which is rich in organic matter and conditioned by earthworms and all sorts of other creatures. This increased in thickness in about the Pliocene to form the first tall prairie communities. Like the other evolutionary events, this was a co-evolution. Grasses, of course, are adapted to being grazed, and their adaptations to that include a whole bunch of adaptations for continuing growth under heavy grazing pressure and driving carbon underground, where it is preserved out of the atmosphere with the result of cooling the planet. The grazers, the increasingly high-hoofed and high-crowned teeth of mammals such as horses and bison are interested in the grasses, and the grasses are interested in the grazers, and they don't care about the environment. What they are creating, though, is an ecosystem which drives carbon underground and which brought on the ice age of the Pleistocene. Here it is in plan, the evolution of grasses in the Cenozoic. In the Eocene, it looks like the situation was very similar to Australia. Australia has no native grasslands. You have them in abundance in South America, not so much in Brazil, but especially in Argentina. But in Australia now, if you go from Sydney, where the forests are, all the way out to Broken Hill, where it gets drier and drier, the trees just get smaller and smaller and smaller. And we have an evidence now from paleosols all over the world, including Australia, that was the case in the Eocene everywhere. In the Oligocene, we start to see something going on in that mid-ground, around about 400 millimeters mid-annual precipitation, where things are opening up a little, where grasses and grazers are co-evolving and creating a molic epipedon as a sponge to take carbon dioxide out of the atmosphere. In the Pliocene, in North America in particular, but also in Africa and Eurasia, that molic epipedon, that surface horizon of granular organic material, increased in thickness quite substantially and drew down carbon dioxide to create the Quaternary ice age that we're currently in, and of course undoing with our own activities. So what I'm suggesting then is that the climate of the planet is controlled by organisms, and that organisms have acted as a thermostat to control the climate of our planet. One interesting puzzle which reveals how this works is a very interesting set of soils that are not far from me where I am now in Oregon. This oxisol, this very thick, 10-meter thick soil profile, which is between 2 basalt flows of about 16 million years old in Oregon. Now, this is really weird. You can see the star there on the map. That's where the oxisol of the Miocene is. But comparable modern soils are mainly in Brazil and Congo. They are primarily tropical. To get an oxisol that far north, something really weird must have happened. This is the middle Miocene warm spot. And we have an idea what happened in the middle Miocene. This is a record going back 300 million years of carbon dioxide in the atmosphere from counting the stomates of ginkgo leaves. And there's a nice fossil one from the middle Miocene there. There's a big spike around about 16 million years when we think that the atmospheric carbon dioxide went to about 588 ppm, which is a lot more than it is now, which is kind of interesting. in the Middle Miocene in 16 million, it appears that the world had an amount of carbon dioxide that we expect we can reach with our own pollution of the atmosphere by about the year 2100. The same calcic spike is revealed by the depth of weathering of calcic nodules there at 16. They get deeper in the soil in calcareous paleosol successions, and the paleolatitudinal distribution of oxysols also increases. The amazing thing about 16 million years is that the oxysols move a great distance from their modern distribution. The modern world, and that is the world at around about 1980, because we've moved beyond the modern world already, as you know, is shown in the top. The red are the oxysols. Look at them. They're all in the tropics only. The Pleistocene world of 20,000 years ago is in the middle panel, B, where you can hardly see any oxysols. There's a few still holding on in Indonesia and in Brazil, but hardly any. And the bottom is the Middle Miocene, when oxysols actually spread as far north as Vancouver, Washington, north of Oregon even, all the way into northern Germany. They were much more extensive in Brazil and down into Uruguay. And they were very extensive also as far south as Tasmania in Australia. Furthermore, we can see differences in mollisols. Mollisols are the grassland soils with that mollic epipedon, that great carbon sponge in green. Mollisols are fairly widely distributed now. That's the top panel. You hardly see them much in the last glacial maximum, but they were much more widespread during the Middle Miocene. This is basically a soil map of the two most productive ecosystems on Earth today, the tropical rainforest and its oxysols, and the grasslands and their grasses. Now, in the Ice Age, of course, what was most abundant were gelisols and iridosols, desert soils of low productivity, and frozen soils or gelisols, and even ice caps, very wide spread. So at times when CO2 rises, the productive ecosystems start to go on the march. They start to expand their geographic range. And evidence seems to suggest that they could actually draw down carbon dioxide within a space of about 100,000 years between those two flows in the Columbia River basalt here in Oregon that have been dated really quite accurately. That is kind of a thermostat. If CO2 gets out of control, these ecosystems migrate and take care of it. On the other hand, how do you stop going into a terminal ice age like a snowball Earth? Well, that happens because when you have the world of largely unproductive ecosystems that are not sequestering carbon, eventually they get overwhelmed because of the continued emission of carbon dioxide from volcanoes, which eventually overwhelms them. The Middle Miocene case of the really large bulk of carbon dioxide was due to a large volcanic province in Oregon, the Columbia River basalts. But volcanoes are continuously putting out carbon dioxide. So we have this interesting soil carbon dioxide thermostat, where the soils with a high carbon dioxide concentration can reduce carbon dioxide in the atmosphere, and the ones with a low carbon dioxide concentration are powerless against the continued injection of carbon from volcanoes and, of course, from our own culture. We need to harness this. We need to learn how to use soils to do this in future. We can actually quantify this. Since we have maps in the Miocene, we can look at the global area of the different soil types, just the four soil types here. For the case of a low CO2 at 200 ppm in the full glacial, for the intermediate case, which is 1980, and for the case of the Middle Miocene, when we're close to 600 ppm, due to this big injection of volcanic materials. The oxysols and the mollisols spread dramatically. the iridosols and the gelisols decline. And we can actually calculate the amount of carbon storage. And the math works out actually pretty well. This was published a couple of years ago to show that the 100,000-year drawdown time is not unreasonable. We would have wished it would have been faster, but it's not. So some problems could be related to that timescale of 100,000 years when we'd liked it to happen within decades, but that's not going to happen. Now, this model I have given you of regulation of climate by soils is somewhat similar to a model that some of you may be familiar with from James Lovelock, one of my heroes. And he postulated this very, very interesting idea that global temperature could be modulated by what he called daisy world. It's a thought experiment, and it's a bit ridiculous, but let's run with it. The basic idea is that there is an albedo control. So if we have two species of daisies, red, or rather black and white, the black ones have the effect of heating the planet because they absorb the radiation from the sun. The white ones, on the other hand, reflect more radiation from the sun than they absorb, and so they have the effect of cooling the planet. The idea, and it can be modeled really quite nicely, is that the black and white daisies will come to some sort of equilibrium to keep the planet livable, because if it gets too hot, then the daisies die, and if it gets too cold, the daisies die. Sadly, this doesn't work for the model that I put forward. I don't think it's an albedo control, and that is because the iridosols and gelisols are the most reflective. They'd be white daisies, and so they would cause a runaway snowball. The grasslands and the forest, on the other hand, are more like the black daisies. They're more absorbing, and they would cause a runaway warming. I think what's happening here in my model is that it's not albedo. Albedo is actually overruled. What's really working is the carbon economy of these soils. The carbon economy of the oxisols and mollisols, the rainforest and the grassland, is such that it consumes carbon dioxide and cools the planet. The carbon economy of the iridosols and gelisols are such that they are powerless to stop the inexorable rise of carbon dioxide from volcanoes, and so they end up warming the planet. Now, I call this idea the Proserpina principle, and the basic idea is that plants cool and animals warm the planet. This is a confusing graph because it's on a log scale. So at one end, you've got just 1 second ago, and then at the other end, you've got billions of years ago. The basic idea is that the primeval high carbon dioxide environment of the atmosphere, which was needed to offset the very faint young sun, has been modulated and decreased with the increase of biological weathering on our planet. And the big steps that we can see in this reduction of carbon dioxide are related to major events in the evolution of life. Life is in control of our planet, and let's hope it remains in control of the planet. Whether humans will remain in control of that planet is, of course, rather more dubious. So this is my last slide, you'll be glad to hear, and it's a lot of writing, but I am not going to read it, you'll be glad. I'm going to sing it. There was a time when Earth was all frozen and glaciers spread to tropical oceans. Even in tropics, the soils had ice wedges, endless piled up on long wind-blown ridges. The snowball Earth, west of the ice ages. What was the reason for such a chilling? Was it the continent's tropical drifting? Was it the weatherable tuffaceous sand, or increased greening of ocean and land? The snowball Earth, west of the ice ages. From Ternian paleosols, the stories unspooling, gypsids transition to calcites for cooling. Pond scum was joined by fungi and others, and so microbiomes consume greenhouse gases. The snowball Earth, west of the ice ages. Well, that's it. Thank you. I hope that worked. I'm not getting any feedback.
Ok, de novo, gente.
Did that work? I got no feedback from my end, but yes, I'm happy to take questions if there are any.
Deu certo? Okay. Thank you very much, Professor, especially your conclusion. I will try that in my classes. Very useful. Thank you very much. I hope we have some questions here. As we are here in a small space, I will try to read some questions. Some of you guys have some questions in the group. Okay.
Is there a chat so I can see it? No, I don't see it.
Is there a chat? But
I don't see it
have
on my screen.
two kinds of transmission. In YouTube, that Renato, you can check the YouTube questions in case, and then there are other questions here in our school. As it's from Gabriel from University of São Paulo, and Gabriel asks, how changes in the configuration of continents have controlled the expansion of paleosols?
Oh, the basic idea of that, it's a sound idea, is that because tropical soils like those of Brazil are so much deeper and thicker, the weathering is more intense. So the fundamental thing about consuming carbon dioxide is that carbon dioxide forms carbonic acid. That carbonic acid then attacks minerals like feldspar and creates clay, and the carbonic acid, the carbon, is then turned into bicarbonate, which is exported from the atmosphere into groundwater. And then it can be buried in sediments of different sorts. So if weathering is more intense and deeper, as in Brazil, that is a stronger carbon sink. In cooler climates, like Oregon, for example, our soils are seldom more than about 1 meter thick. In Brazil, for example, the carbon dioxide content of the soil itself can reach 104,000 ppm. 104,000, that's extraordinary. In Oregon, pretty typically in Western Oregon, we get about 5,000 ppm. In Eastern Oregon, we get about 2,000 ppm. That means the concentration of the acid is much lower. And so the degree of weathering and the rate of carbon consumption from the atmosphere is much slower. In Brazil, of course, you have a temperature that's really very warm, and for any chemical experiment, if you warm it up, the reaction goes faster. In Oregon, the mean annual temperature in Brazil, I think, is something like 20 degrees centigrade or 25 even. In Oregon, it's more like 10. And so we actually have an order of magnitude slower chemical weathering reactions in Oregon than in Brazil.
Thank you, Professor. Guys, as you're having questions, you can send by our groups. Vocês podem escrever no nosso grupo, eu traduzo, ou pode ser em inglês, okay? Professor, I have a question. Almost everything that we are researching Precambrian is so reliable to investigate life beyond, life in other planets or other moons. And now we have all these missions of investigations and even collections from Mars regoliths. But we have a kind of polemics about the concepts of soil and the difference of among soils, between soils and sediments.
Yes, of course.
And as I see, maybe if we perform more profound researches on soil science, maybe we can improve the biogenicity criteria.
Right.
Um,
Yeah.
Considering microbiomas, etc.
Yeah. This book here over my shoulder, Soil Grown Tall, is my latest, which deals with this. For a more popular audience, your audience might be interested in seeing that. But yes, the question of how to define a soil is has been a contentious one. Some people think that you have to have life for it to be a soil. I do not, and I started out with the odd view that soil is a material that is altered by physical, chemical, or biological processes, all three. Now, if you take that view, then it's quite relevant to whether you regard the Martian surface as soils, which I do. I believe the Martian surface is a soil for the reason that it certainly shows physical weathering, and it certainly shows chemical weathering. That's been demonstrated by the Curiosity rover. Now the question becomes, was there life in the Martian soil? That's how I would put it. Not did the regolith support life? No, the regolith is a confusing term, and it's particularly confusing because if you use the word regolith, that means both sediment and soil, and we really want to distinguish the two. I think there is evidence that there was life on Mars from vesicular structure and a few other things. And furthermore, the life on Mars appears to have been gypsids, like what I described from the Precambrian already. There's a big difference between sediment and soil. Sediment is just dirt. It's soil out of place. So sediment is, I think, the yang. It's the destructive forces of the planet. Soil is the yin. Soil is building. Soil is in place. Soil is weathering. It's slow. It's purposeful. It has a direction. It has a lot of properties of life by itself because the soil is born usually on a fresh sedimentary surface, and then a soil develops by having more and more calcium carbonate nodules or more gypsum crystals in it. And the soil gets to old age, and eventually it dies because it's covered over. This yin and yang property of soils versus sediments is an important distinction that is really critical for understanding the thermostat that I've outlined. But yes, there are some people who stick to their definitions. The other difficult definition, of course, is how do you define life?
Yes, we don't have a definition yet. Yes, it's very
NASA has struggled with this for many, many years.
Yes.
And the current definition. So I went on the soil definition one. I put out this definition of physical, chemical, or biological a long time ago, and people are now on board with that by and large. NASA now defines life as a system which is capable of Darwinian evolution. In other words, evolution by natural selection. And a sedimentary system is not capable of that, nor is a mineral system capable of that. The cooling of a granite and the formation of underground amethyst cavities like you get in Uruguay, no, that's not a system that can evolve by Darwinian evolution, but soil can. So what happens when a soil starts to develop is that it makes more clay and it makes more cements, it makes calcareous or gypsic. And so that is a natural selection for it to be able to persist at the surface to make more clay and more. It's naturally selected for its own persistence. You imagine an early world in which salt was starting to form clays and starting to form these common cements of soils, particularly calcite and gypsum. Those places where those formed the most preserved against the forces of erosion. So in this model, it's really yin and yang, isn't it? The floods and the windstorms, they are going to destroy the soil. The soil, on the other hand, is trying to build and hold its place in the sun, where rain can weather the minerals and where carbon dioxide can effectively create new soil minerals. So I see it as this titanic struggle that it's yin and yang, male and female. It's soil and sedimentary destruction are opposed forces, and it's the balance of the two that have created the thermostat which is found on our Earth.
Okay, great explanation, Professor. Thank you. We have another question from William from University of São Paulo. The productivity of microorganisms is related to the consumption of CO2 and production of O2, which is related to variations in the ocean's pH. This in turn would have an implication in the formation of oxidized iron and manganese minerals. The question is there a pattern between the geological record of glaciation periods and the records of the formation of iron manganese oxides and hydroxides?
Oh, absolutely. Absolutely. So the big transition between prokaryotic and eukaryotic systems was actually long before the Snowball Earth transition, long before the Tonian. The big transition was at 2.4 billion years ago. We have evidence that eukaryotes first came into the system around about, well, the oldest one I know of is 2.1 billion years old. It's in a paleosol in South Africa, and it was a eukaryotic fungus-like thing, quite similar to the living geosiphon. It was an oxygen producer. So, yeah, of course, the development of eukaryotic soil systems, starting at about 2.4 billion years ago, oxidized the planet. They had photosynthesis, which was oxidizing. Before that time, the soil microbiome, which we find preserved as microfossils in paleosols, was largely sulfuric. We find that the soils are full of sulfate, which means sulfur has been oxidized, but also has a lot of sulfide. And the sulfide is original. That comes up with basalts. That's found in igneous rocks. The sulfate is something original that's found by biological oxidation of sulfide, but that does not happen necessarily in a highly oxidizing atmosphere. Back in the Archean, we also have banded iron formations, as the questioner probably knows, and those are from the biological oxidation of iron by microbes. So the basic trick that microbes use to reduce carbon dioxide, which is the stuff that's coming out of volcanoes and was very abundant early on, into organic matter or organic carbon, is they oxidize some mineral in like a coupled reaction to reduce the carbon of carbon dioxide. In the Archean, we had anaerobic oxidation of sulfur and of iron to produce some oxides, limited amounts of oxides, in an anaerobic atmosphere with very little oxygen in the atmosphere, mainly by prokaryote organisms like sulfur oxidizing bacteria and iron oxidizing bacteria. By the time we get to 2.4, we've got eukaryotes, which require a lot more oxygen and also produce a lot more oxygen. So we have fungi, which require more oxygen, and we have algae, eukaryotic algae, which produce a lot more oxygen than cyanobacteria. Cyanobacteria eventually learned the trick too. Cyanobacteria can be both anaerobic and aerobic. So this has to do with the evolution. These microbiomes controlled the evolution of our atmosphere.
Another question, Professor, is if you have to advise the future missions, spatial missions, to deal with the problem of weathering in the identification of biominerals or organic matter, because I think that it's very challenging for perseverance, for example, to detect some biosignatures in Mars soils. Maybe because of weathering or because of the types of clay minerals, I don't know. The kind of methods and techniques that are applied are very advanced, but we still have some problems with the kind of sample that are analyzed. So if you have to advise NASA for the future missions, what advice would you choose?
Well, I'm a geologist, I like rocks. I like things that I can see that are easy to understand. I like to be able to interpret soil profiles, whole soil profiles. And yeah, I do microscopic work. I look at them in thin section. I can run geochemistry, just bulk geochemistry, and isotopes on them. That's the sort of toolkit that I have as a geologist. But we live in a big scientific world with a lot of fancy instruments now, which is really quite remarkable. There's a whole group of people who have the fancy instruments who can characterize the microbiome at a genetic level now. It's quite remarkable what they can do. They can tell you everything that's in that microbiome sample in a modern sample. And they are also very interested in paleosols, in what could have been there. We're getting more and more interested in what's on Mars. So I was on the red team for the Mars, the new one, the one that's in Jezero Crater, the new rover, that's going to return samples. So my role in it is to try and find where the paleosols are and where to get the best samples. And my students are working on that. But when we get them back, then a whole bunch of other people will take off with the fancy instruments and figure out if there are traces of a microbiome in the Martian soil. And today, people are starting to get a much better understanding of the microbiome of modern soils, even on Earth. The Atacama studies, for example, which I've talked about, have been really well informed by these microbiome studies. We're starting to link whole ecosystem productivity to knowing actually what's in them. This is all new. It wasn't available when I was a student. Now, some students may want to carry on and do that. That's not me. I'm interested in the basic questions and in things I can see. But the modern tools that we have now are really opening doors. And the people who have those fancy instruments, they're interested in big questions. The big questions come from people like us, not from other people who are just doing microbiome studies. The interdisciplinary nature of science has proven over and over again that the big discoveries come at the interfaces between different disciplines. So we live in a really interesting time when you really have to wonder if we can save the planet or we'll go down with it.
Yes, the big discoveries came from the interfaces. It is a great point. I believe that now do you guys have some questions? It's okay. Professor, thank you very much for your talk and all these ideas that we discussed today. All the students are very thankful for your participation, and we can keep talking in other events. I hope so.
Thanks so much. If they're interested, my latest book, which is called Soil Grown Tall, it's on Amazon. You could probably have it in your library.
Okay.
Yes, Soil Grown Tall. The cover is, well, there it is. It's got my wife on the cover.
This one we are able to see. We are looking for your book. Thank you very much.
So all these ideas are in there.
If you can send us the reference in the email.
Sure.
There is another question.
I'll email you the link to Amazon. Yeah.
There is another question here, Professor, that we have,
Oh, okay.
if you have time, last one.
I do, yeah.
Mauritius, postdoctoral researcher at Federal University of Rio de Janeiro. Maurício, please write your question.
I didn't catch that. What profession? What?
There is because we are in YouTube as well, so there was another students asking questions in YouTube. But Mauricio, maybe we can wait for the Mauricio. Is in YouTube? No.
I don't understand the question.
No, he will perform the question. We are checking here.
Okay.
Tá no YouTube?
Tá no YouTube, mas eu não escreveu.
As we wait for the question, Professor, if you please can send us the reference of your book.
I will, yeah.
Yes. So I let the students know about the reference.
Mm-hmm.
Okay. Mauricio is not writing the question. So we will finish here, Professor. But thank you very much for your time and the talk and all knowledge that you provided us today. Thank you very much.
Lovely to meet you all. Thanks again. Bye-bye.
Bye-bye.